All right, there we go. We are live. So let me just start recording this for our YouTube channel, and then we will kick things off. Hello, everyone, and welcome to the next episode of Zymposium, Building Better Open Source. Returning to this episode after a few week hiatus is Cameron Smith, who is a computational biologist who's working on a very interesting open source platform called BioRoastery. And we have been working with Cameron back and forth on figuring out if and how the architecture and the design of BioRoastery can benefit from the WASM component model and maybe durable execution, because there are lots of, I think, really compelling reasons why a system like this needs to be very reliable and very scalable and very secure. And we talked about many of these reasons in the past few episodes that we had together. And we're trying to see if there's a way for us to benefit from some of this next generation technology and architecture. And then what we did in our last session, I think, was we took a look at a specific part of BioRoastery that involved downloading data sets. And I had come up with some pseudocode and a sort of straw man architecture for here's how I would think about doing this on an open source platform like Golem, which gives us durable computing, as well as the security and sandboxing stuff that you get out of WASM. And let's go back and get your impression of that sort of straw man architecture and the pseudocode I sketched out. Do you think there's something here?
Yes, absolutely. And I think, you know, in terms of some of the potential implementation details, obviously, we'll have to think through carving things at the joints to best interface between the various sort of target languages that we have available to us through Golem and through WebAssembly. But I think in terms of the architecture itself, I think is fantastic start and illustrates even in this seemingly relatively simple case already, I think potential value of taking an approach that uses WebAssembly and even durable computing. And some of the reasons for that we discussed last time are really simple. Um, a couple of which are things such as downloading large data sets via giving access to many people to download very, very large data sets could be very costly if things are failing and restarting from scratch over and over again. And so I think this, among many of the other advantages, are reason enough to continue pursuing the experiment, and exploring how we can best integrate these types of components. But I don't know if I should give a one more 2 sentence review background of where we started with the project and why I think it's interesting and relevant, maybe before we switch back
Absolutely.
into discussing the
Absolutely.
architecture.
And if nothing
Um,
else, you can practice your elevator pitch, which will get
yeah,
better.
yeah,
The more times you
yeah,
practice your elevator pitch for your open source project, the better that's going to get.
yeah, absolutely. Appreciate the opportunity to do that. Maybe I will share my screen at least
Sure.
briefly here again. So yeah, the concept for BioRoastery, as John mentioned, is very simple in many ways. It's to provide a sort of reference architecture that people who are doing both infrastructure and model development work can use to provide a service to people who are less computationally inclined, that allows people to do a wide array of analyses that may be of relevance in bioinformatics. And so, as I have mentioned in each of the previous discussions, there are many tools out there that do things like this, but none of them that has the depth of availability of both all of the infrastructure code and all of the model implementation code that we're planning to put together in an open source, a fully open source package. So that includes everything from the sort of, Kubernetes configuration with Q, and which gets sort of turned into YAML at some point in a way that's somewhat has some features like you would expect from type safety, even in the configuration domain. Implements a sort of Argo CD managed GitOps cluster, and then deploys various services on the cluster that perform some of the features that are really common in architectures, as John has mentioned several times. A sort of proven architecture template that I sketched out before we started here. And so we were discussing where could we start by implementing one of these components, or one of the relevant components that maybe isn't fully represented here, using Golem. And then as we walk through some of the other components of this architecture, how might we rethink some aspects of this? And so, as John was mentioning, the component that he so graciously spent his time to put together a prototype of was a component which was meant to sort of download, concurrently chunks of relatively large genome sequence files from publicly available databases, in a way that would be, robust to all the sorts of faults that we've come to expect from, public hyperscaler based computing, in addition to, the fact that we would just like this to be efficient in general. So just to, I can let you share your screen if you want, since this is your work, again, but just to review, where we were. John had sort of proposed this sort of an architecture for just this service to help us manage, downloading very, very large, or not very large, but on the order of, let's say, 10 terabyte files in our first target case, and doing it in such a way, which is probably the most interesting part of the proposal, that we could perform a few pieces of computation while we're streaming the data in to our own managed sort of object storage, which would be hugely advantageous because maybe we can both parallelize many of those computations, which, again, for anyone who has any exposure to the domain of interest in this case, would be taking these genomic sequence fragments and mapping them to a reference genome. So we could do this among potentially a couple of other things while we're streaming in the raw data. We're going to, cache the raw data so that we always have sort of a provenance and lineage tracked for, what we're working with. But we may be able to reduce the file size that we need to work with in any of our downstream sort of steps in our workflow by at least a factor of 10, if not more, by by performing some of the initial pre-processing that we need to do while we stream the data in.
And I think also with this architecture, we are in theory able to reduce latency because we've got that massive amount of information coming in for the first time. It's in memory. So why not do as much as we can with that fragment of data? And as we're just streaming this information in, the only thing we can do is basically a filter and a map. But that's still a lot. There's still a lot of really interesting things I think you can do with a filter and a map. And that's just going to cut down on the amount of time necessary. That plus the total reduction in data that comes about through the filter is going to significantly, I think, cut down in many cases on the amount of time necessary to run one of these workflows on a really big data set.
Absolutely. And yeah, I think that already illustrates, an advantage is even when we get, this large data set into our own object storage, we'd rather avoid ever touching it again if we possibly could. And so this sets things up in such a way that that's conceivable. And so I think, that alone is a really nice, obviously, yeah, we're also, reducing, obviously we'd be downloading these files in chunks and so forth, insofar as the APIs we're sourcing the data from support it, which seems to be universal for most of the data sets that we're interested in.
So we did this.
Yeah, we did this, and unfortunately, I failed to take a stab at implementing it. So I apologize to the audience, but I am going to put myself on the hook to do that in the near future, hopefully before we do our next meeting, so that we can actually discuss what will probably a secondary failure to to actually implement John's specification here, but at least I'll have enough of
That's the boring part.
details,
Well, maybe
enough
not
of the
boring, but
details of the failure that we can discuss them with some interest, and also continue to add to the growing body of examples of people implementing things in Golem, which
yeah,
will be useful as well.
that's right. So in this session, I think what we should try to do is we've seen a little bit, I would say we've seen a little bit of success. We've seen that there's a fit between this problem domain in computational biology and the fact that it's scalable and needs to be secure. You're working with a large data set. You need reliability. Reliability helps reduce latency and so forth. We've seen all of these different problem requirements have a really nice mapping onto durable computing using WASM for different reasons. Like the WASM gives us the sandboxing and the ability for C to like talk to Python and so forth. And then durable computing gives us reliability, and something like Golem gives us scalability. So there's a really good fit. And we ended up, I think, in this download component, as simple as it was, I think we saw, yeah, it looks like there's something here. It looks like there's some benefits. So now perhaps what we do is we take a step back. And in this session, we look at the big architecture, not just the little download component that we took on in our last section, but we look at the whole thing. And we say, well, if we were to architect this specifically for a platform like Golem, which gives us durable computing and the benefits of the WASM component model, how do we do that? What sorts of changes would we make to this architecture? And what would the effects of that be? Would it be better in some way? Would it be easier to implement, easier to maintain? Would we gain the capability to do things we couldn't do before? So I think what we should do with the next 45 minutes is explore that topic and come to a conclusion. Like, did we go enough or did we not go too far? Maybe we need to try to think about doing all of this in Golem, or maybe not. Maybe we did the best component we could possibly do in Golem, and the rest should be this sort of traditional proven architecture that you initially came up with. Does it sound like a plan?
Yes, absolutely.
All right.
And I would also just mention that in doing that, one thing we can explore is this box here, which is referred to as workflow execution, is hiding away a tremendous amount of detail. Whereby the first component we've discussed, which is this sort of data ingestion service, begins to interface one by one with the components in what are relatively simple workflows inside this box. But each of those components could conceivably be another one that could benefit from at least exploring the possibility of implementing it with Golem. And so, if we want to delve into any of those slightly more detailed components, we can even pull up the code that continues on from the that illustrates one of the things one might do, after this data has been ingested and a certain amount of pre-processing has been performed. But we can also discuss any of the other components, because there's obviously another end to this, which is to eventually be able to provide, to back front end services, which, have their own obviously complexities involved as well.
That's right. All right. Well, there's one thing that occurred to me when I first saw this architecture, and I've been thinking about ever since. And that is, it seems to me that with this type of application, you might benefit from some sort of plugin architecture, whereby like third-party developers who have that background we talked about in computational biology, but also the one in computer science, so they can actually write really good code, are able to build plugins that can then be snapped in here. And the reason I'm thinking about that is just because of all the different types of variation. It's not like every workflow needs to do these four different things, right? It could be quite different. And the requirements around that have to be flexible as people come up with new ways to analyze and join and enrich data. And so that suggests to me that either there's tons of one-off code, like everything is one-off, or you have some sort of architecture that can factor out the common parts and then leave the use case specific parts to the developer for that particular use case. And that leads you to a plugin architecture. So what are your thoughts overall on a plugin architecture being the solution to the variation that occurs in analyzing these large data sets?
Yeah, I think that's almost surely um, the right approach to take, certainly at the level of this concept that, although I mentioned that this is hiding complexity,
Yeah.
the workflow execution box, it's also something which could be swapped out with very, very, different, graph structures
Yes.
that you may want to compute. And so, I think obviously handling the details of how you actually proceed and execute the subcomponents of the sort of mostly DAG workflow uh, structure here is definitely something which is amenable to then saying, well, I can provide potentially a plugin that or a developer, as you mentioned, separating out these two groups, people who are more oriented toward development can provide plugins potentially that begin to specialize beyond just, oh, I have a DAG workflow execution engine,
Yes.
and but don't go all the way down to hitting every single byte that's passing through the system.
That's right.
And so I think from that perspective, this is definitely the right sort of concept to think about in terms of enriching and providing a good potential community building architecture for this backend
Yeah.
component where you can take the division of labor that inspired my thinking of this architecture and really try to incorporate that intrinsically to the structure. So I think that I don't, but I'd be interested to hear more. And this, I'll turn it back to you on this point as to, yes, what level of abstraction would you imagine in terms of designing these plugins? How much can we, imagine being able to provide completely generically so that even the plugin author, doesn't need to rebuild, things
Yes.
that are doing DAG workflow execution? How much of it should be we're handing this, sort of API off to that type of a person?
Yes. That's
Yeah,
right. So I think we'll return to that topic at some point. But
sure.
one of the ways I like to view plugin architectures is how much of the like baseline system itself can you implement as a plugin? Like, can
Mm,
you get things down to this level where you have this tiny amount of bootstrap code that's like the skeleton that holds things together, and then all the features that you want to bake into the platform are actually implemented as plugins? And it's not quite similar, but it's related to some work I did for this open source project called Zio that I work on. And basically in Zio, I tried to find a tiny little core that I had to implement. And then I implemented the rest of that in terms of that core. And I would implement it in such a way that, like, if there was a part of that that I had to implement low level, I would do that. But then the rest of that, I would sort of dynamically rewrite that to more Zio. And that ended up allowing me to have almost like a microkernel that I can audit for correctness and security and all that stuff. And then the rest of this stuff was just sort of unfolding into that microkernel. And I really like that architecture. And I've done that before. And I think in something like this, we can imagine what would that plugin architecture have to look like such that the baseline set of features that you would want to ship with this platform without any plugins are actually secretly, not to a user's perception or way of thinking about this application, but they are in fact plugins. What that does is it just sort of strips the essence of this platform down to core foundational essential elements, core number of operations and data types and whatnot on which the rest of the system can hang, and making it sort of self-bootstrappable in that sense, where core pieces of the functionality are implemented in terms of the lower, more primitive level. But before we do that, I'd actually like to take a closer look at the architecture and ask you some questions about why there are certain different pieces. Because if we're thinking about doing the whole thing, I think that plugin part you can see is probably going to be doable with WebAssembly component model. And I think you could also see that it might have some benefits in terms of like Python calling C and Rust calling Python, all that sort of cross-language stuff that we talked about before. There's another element there, though, which is the security sandboxing. Like you are sort of running untrusted code on your platform. So how are you going to make sure that that doesn't interfere, at the very least, doesn't interfere with all the other background analyses that are going on? And you also might have to consider, I don't know, you tell me, you might have to consider, do you need to keep one workflow separate from another in the sense that they should not be able to access each other's data? Is that the case?
Um, that's probably that's probably a safe that's probably a reasonable assumption to try to incorporate. Yeah, from the
I mean,
beginning.
on the one hand, you
What
might
would
say
be
it's
the
all open
advantage?
data, and it's
Yeah,
like,
I mean, what would be the, I guess I would flip it back and say, what would be the advantages that you could imagine of allowing them to access each other's data, if there are any that come to mind?
I,
Yeah.
I don't see that at
Yeah.
all because, okay, they're using a public data set, but let's say they upload a private data set that's related to, they're at a company maybe,
Yeah.
they're working on something that's secretive. And it just seems to me like you would want it to be so secure that my running workflow has no way, like there's no actual way for it to access the data of any other workflow.
Right. Yeah, I think I think that is important in the end because the other reality here is that most of the target audience, I can at least come up with a macroscopic prediction of the size of their sort of a potential user base is going to want to start with public data and
Yes.
eventually integrate it with something that's at least initially potentially still private. So I think we
Like
would be.
pre-research or pre-publication, right? You have some data. It's going to be public
Yeah,
eventually. You're still playing around.
but yeah, also the obviously even governments in the pharmaceutical industry, they always are. We want to get as much as possible, of course, out of the public data,
Yeah.
but then we want to see what that can add to some slightly more bespoke data that we have at our disposal. And I think also just naturally the way that the component model provides the ability to do
Yeah.
this isolation, it makes sense to, I think, feature that if insofar as we're going
Yes.
down this path. So yes, I think yeah, I think I can't imagine there are probably some cases where you could get some sort of performance boost if you were really clever about sharing information between
Yes.
them. But I think we can forego that because it also kind of in a way simplifies it and is more natural in terms of, yeah, as
Yeah.
far as I understand it, at least how the component model is designed to
Yeah. I
support
think it's a
rigorous
natural
isolation.
fit. And
Yeah.
without that, you're basically looking at containerization technologies or virtualization or something to get that level of security. But
Right.
we sort of get that for free using the WASM component model. So it seems like why not? Why not? As long
Right.
as
Right.
it's valuable, why not take advantage of that and also think about that as we're doing this architectural work?
Yeah, absolutely.
All right, so let's take another look at this architectural diagram, and then I'm going to ask you just a few questions on some different components here. So
Sure.
I'm not surprised to see Kafka sitting at the almost like the literal center of this architectural diagram because in so many distributed applications today, Kafka is the center. It's the beating heart of the distributed system or something like Kafka. So
Right.
however, there's like a bunch of reasons that you might want to use Kafka. And one of them is you just need persistence of intermediate state. So that's like more event sourcing systems where They want to persist at every tiny little bit of information so that if there is some failure, it's not going to affect the overall operation of the system as a whole. And might be one reason that Kafka is sitting there. But then there's several other reasons. Another one is you just want to decouple producers from consumers. So you have a finite amount of compute and memory associated with that, and you have all of the sort of incoming requests to do more workflows. You got to partition what you have among all the available demand that's initiated in the front end here. And one way to do that is to use a queue, which allows you to sort of loosely couple production from consumption. And so you might be using it for that reason as well. And then another reason that people turn to something like Kafka is they want to distribute work. So they want to say, we're going to dump a bunch of work into Kafka, and that's going to be processed in parallel by a bunch of different systems or nodes or whatever. And it's possible that you chose Kafka for all three reasons, because I could see that as well. What are your thoughts on why Kafka is the beating heart of this architectural diagram?
Yeah, I think all of the above with the one caveat that I was imagining that there would be a sort of a separation between the case where, let's say, we have two users who are both working through the front end. They both want to fire off, a certain number of these workflows. We have a certain computing budget. Um, I was thinking that Kafka would essentially serve as the intermediary that would almost immediately, though, uh, excuse me, dispatch to the workflow execution engine that I've been using so far, but that it would do so in such a way that it wouldn't obviously just allow firing off an infinite number of these workflows.
Yes.
There are obviously some other applications that, if you really want to scale the front end, where I think Kafka can become, relevant to fire off even much smaller,
Yeah.
jobs and coordinate computing. But insofar as I was, sorry, I keep clearing my throat, envisioning it so far, um, I was sort of imagining it more as just an intermediate layer where the workflow execution engine doesn't necessarily have any information, yes, about, oh, there are 30 workflows running. It just knows, okay, you triggered a workflow. I'm going to try to run it on what's available. Whereas Kafka would kind of stand in between and say, look, this, user has requested to run 57 workflows, but based upon various models of how we want to allocate resources, maybe they'll only be able to run 10 for now, and then 30 of them will remain in their queue, and they'll get notified when they're allowed to be released to the workflow execution engine. So that was
Yes.
the really pedestrian perspective in which I was
Yes.
imagining to be that Kafka would be something we'd want to start integrating. But I'd be really curious to sort of re-envision that through the lens of how you might think of doing it, with tools like Golem.
Yeah. So Golem encourages you to think in terms of workers, and workers are not just like AWS Lambdas. They're way more than that, because an AWS Lambda, you can call it, you can trigger it, and that's it. It does its thing. It has to live short. Doesn't really have durable state or anything like that. But a worker is just an instantiated WASM component, so it has its own API. And a worker, once it's started, it can actually run forever. And you can keep calling into it and asking it to do different things or querying it and whatnot. And these are just different functions sort of exported by your running instance of that component. And so when I think about architecture for Golem, which is admittedly new to me because Golem itself is pretty new, so I'm still figuring out how to translate all of my knowledge of these enterprise scale architectures to Golem.
Right.
I'm often find myself thinking in terms of workers. And an easy way to solve some of the issues that you raise here is going to be to have a workflow manager. Let's call it a singleton worker. And I'll explain why I think that's okay in a second. But singleton worker means there's exactly one workflow manager for the entire system, no matter how big it is. Maybe it's running on 1,000 nodes, doesn't matter. Only one of those nodes is hosting the workflow manager. And
So
then
could we say, sorry to interrupt you, but could we say this is analogous to a very, very rough approximation to the concept of the download supervisor that you proposed
that's right.
last time? Yeah. Okay.
That's right. And you had like per download, you had a single download supervisor that was then in charge of all the other workers that would be spawned off
Yeah.
in an attempt to do this single download. And in a similar way, but actually, that's not a singleton per se, it's a singleton per download. So there's only one of those per download, but there are multiple of those depending on how many downloads are
I see.
happening currently. And in the case of the workflow manager, I'm imagining just a single one of these workers that sort of sits at the top. And its job is to accept all of these requests that are coming in to kick off these workflows. And it's not going to do any significant work itself. It's just there to look, keep an eye on things, and then implement whatever policies you decide are useful to ration available resources. And an example could be the workflow manager could sit there with a relatively dumb queue, which is just like an in-memory array or whatever, and all of that is durable state because it's running in Golem. It just sits there with that in-memory queue, and it's like we're going to allow 5 workers to, or 5 workflows to run, 5 concurrent workflows to run at any one time. And until one of those finishes, we're not going to start the next one. And so it's going to be in charge of not only kicking off these workflows, but keeping an eye on them and getting notification when they're done so that it can make new decisions about what to kick off next. And the policies doesn't have to be as dumb as queuing. It could actually be much more sophisticated because you might want to look at things like the size of the data set, the complexity of the computational analysis that has to happen. And if you have like this sort of standard library of different types of workflows that you run or analyses that you do, then you'll have some estimation of how complex is it to run this. And then you already have the initial data set size, perhaps, or that's something that you could easily expose. So the workflow manager could look at those things, but it could also look at per user quotas. Would you really want a single user to be able to spin up, get 1,000 slots in the queue and basically hoard all computing resources for themselves until all of those? You probably wouldn't want that. So you might have some notion of fairness. Like we're going to take one of yours, but then we're going to take 999 of all these other people before you get the next one. Something like that. Anyway, you can implement all of that as code, right? Ordinary code using in-memory data structures. So the workflow manager is actually going to be very simple. It's just going to have a bunch of in-memory data structures and some initial data, whatever you know about the workflow, and then it's going to make some decisions about which to kick off and which to hold around in memory until later. And you can even do things like expiration. Like maybe if a workflow has not had a chance to run for 2 days, it's time to kill it. And maybe you don't just want to kill it, but you actually want to send a notification to that user saying, sorry, but we're too overloaded. Try again later, something like that. It all becomes very easy to manage because it's all in-memory data structure. It's all ordinary business logic. And you don't have to worry about persistence. You don't have to worry about any of that. And you can count on that workflow manager to always be running. Doesn't matter what happens with the architecture. Doesn't matter application updates, CPUs going down, nodes being removed. None of that matters. That workflow manager will always be running somewhere and always have all that state in memory. So it becomes very easy to create very sophisticated workflow policies that would be hard to replicate using just Kafka. Plus Kafka is serialization, input, output, all this other stuff. It's more infrastructure to manage. So a lot of these functions that you were using Kafka for, I think, could be provided by a workflow manager, which would actually give you tremendous power and also simplify the architecture and the code and the infrastructure, everything. What
Yeah,
are your thoughts on that?
Yeah, no, I had three thoughts that came up. One was that, my intuition was that even though I think this is roughly how many people might propose to set this up, for the purpose I have in mind, I totally endorse the concept that it's extremely heavy-handed, at least at first, to be in baking in a total dependency on Kafka, at least if the only purpose is to, manage the sort of
It's used a lot for managing
yeah,
workloads. It is, and it's
yeah.
good
So
at
I
that.
yeah, but I think the second thought I had was what I like about what you're proposing is it sort of takes, if I, to the extent that I've understood it correctly, we have the concept of, I was thinking last week when or the last time we held the symposium, when you mentioned the download supervisor, the funny thing was my initial inclination was, well, what do you mean there's only going to be one of them,
Yeah.
because that thing's, but I know, but at the same time I knew in my mind that, I should, yeah, but actually the fact that there's one of them, given the guarantees that you get with Golem, means that there will be one of them, and
Yes.
so when you just started discussing the concept of, yeah, we'll have a single workflow manager for this complicated system, my initial condition, what do you mean we'll have a single one? It's going
Yes.
to just fall apart. But then I have to remember, no, a single one means a single one in this context. And so then what I really like the third thought kind of combines those two that I really like is that I can already begin to see with the simplicity that then allows for there to be one thing to perform one function. I can already see how eventually what would likely I can imagine happening with this architecture is what I would sort of have wanted to happen, which is I don't necessarily need a complex system like Kafka and a separate complex system, which helps to sort of abstract some aspects even of Kafka, like Dapper, and another complex
Yes.
system like the workflow manager. Over time, I think if I replace, for example, if I say, look, what I'm really using this for right now is this, sort of queuing system for firing off workflows. At the beginning, just like with the download service kind of being
Yes.
semi-independent, I could say, look, okay, now here is this service that's going to actually, manage the queue for executing workflows. However, the way that it's structured is almost exactly like the individual components of the
Yeah.
workflows themselves. And so I think over time, I suspect if if I can begin implementing, like, let's say these two examples now, I think we're sort of venturing into the concept of another example, which is we've got the data download service. Now we're thinking about, yeah, how do we actually, design a worker to serve as a queue manager of sorts for the
Right.
workflow engine. So far, I haven't touched the workflow engine. However, in the back of my mind, immediately, the way that you're discussing, designing it in terms of individual workers, I can see how eventually we can experiment with which of even the components of the workflows could be swapped out with Golem components, so that in the end, the whole thing sort of has a monolithic, a uniform rather structure,
Yes.
in terms of each of the components really is just the same thing, and there can be as simple as precisely what it is that they're being used for, or as
That's right.
complex as they need to become in the future. And so, yeah, I definitely, yeah, I think that I would have to, of course, think through, as you did for the download service, in much more detail about how that might actually
Yeah.
work. But I can begin to see even how, yeah, there's some shared opportunity, because the architecture is or not the architecture, but the way that you implement workers is going to be uniform when you're
That's right.
using these tools. Like,
Now, because
yeah,
I'm suggesting a single worker for the whole cluster for all workflows, I think it's worth thinking through the implications of that, just making sure that that's reasonable.
right,
Basically, how many workflows could be handled by a single worker? And my belief, correct me if I'm wrong, is that the number of workflows submitted to such a system would, even in the sort of wild success of this platform, you can't imagine it being higher than like dozens per second.
right, no,
So dozens of workflows per second. That's so easy to handle with a single worker, right?
yeah,
You don't even have to justify that. If you were saying we need to reach 20,000 workflows per second, then
right,
okay, you're going to have to start thinking, about distributing that over more than one worker. But dozens per second is no
Yeah.
problem, no
Right.
brainer. I don't even need to scribble on a napkin in order to justify that. It's just obvious that it's going to work. So dozens of workflow initiations per second, does that seem reasonable?
Yes, and yeah, like it's not like we're doing financial transactions and so forth where
Yes.
so much of this would become an issue. And yeah, we're in that middle ground where dozens per second would essentially never be a bound that would be crossed. I don't think if
Yes.
it did, it would be something that the situation would justify rethinking what needs to
Yes.
be adapted. But that would be a huge success if you got anywhere close to that, as you said. So yeah,
Fantastic.
yeah.
And then the other thing is how many unexecuted or rather pending workflows would
Mm,
we have at any one time? What's the upper
right.
limit on that? And I could say, definitively that we should be able to handle in a single worker, we should be able to handle easily, easily hundreds of thousands, I would say. If we're using efficient in-memory data structures like maps and whatnot, and we're watching exactly what we're storing, like not storing too much metadata and whatnot, then hundreds of thousands would be fine. And tens of thousands is like easy. I think I might have to justify the hundreds of thousands. I think I can do that. But tens of thousands of in progress, uncompleted, pending workflows is no problem. It's super easy to do that. So
Right.
is what are your thoughts on how many workflows are like right now currently scheduled for execution or pending, not yet done now? Is tens of thousands going to be enough?
Yeah, I think so. I was just trying to think of that in terms of breaking down where that number would come from. So let's say we had, you know, 100 even 100 active users on one instance of the platform,
Yeah.
uh, and those users are submitting even somewhere between 10 and 100 workflows a day. So even if there was no progress through the system, yeah, 100 users submitting 100 workflows, uh, you know, in a day would give us a queue around 10, at 10,000. And so I think that's like a very good sort of design threshold to start with. I don't
Yes.
think that uh, that threshold might get broached before the 12 per second submission.
Yes.
But again, it would be a huge success if it was pushing anywhere near that. And so the concept that you could handle that volume, yeah, with a single worker is pretty incredible in a way to me. But it's certainly a great starting point to say, yeah, we can prototype for that sort of design constraint and see what we need to change if it needed to be improved. Yeah,
Fantastic. So I
yeah,
think that's a reasonable architecture. And I would estimate, the bound as probably being, at 100,000 pending in progress workflows, you've got to think about what comes next, and that architecture would have to scale and basically split up the workflow manager into different pieces. But I think, upper bound of like 100,000, and that's with being a little bit careful about how you're storing those and making sure you're using maps rather than dumb lists and arrays and whatnot to store and manage these workers. You're going to have to be a little efficient in sort of indexing this information on whatever criteria you're using to make the decision that we need to launch more or we need to put these in a holding block for a while and launch them later. You have to be a little bit smart about that, I think, to get at the upper limit. But I would say 100,000 in progress workflows could be supported by this up to.
why
And
why
then
is that the why it just what is the first thing that's going to provide the constraint? I'm just curious what you have in
you're
mind
going
is
to
going to
run
be
into two separate things. And the first one is just the amount of memory that is going to be consumed by this worker.
right.
And even though that could, in theory, be great, if you're running this in Golem, it's basically going to try to start the memory at, I think, around 512 megabytes and only grow it if it needs to. And then
Right.
also you have the issue of, Well, other workers coming in and being executed on that same node, that might put a little bit of memory pressure. And right now, Golem doesn't have an ability to say, this one is consuming, 2 gigs, so we're
I
not going to
see.
host anything else on this machine. It doesn't
Ah,
have that
okay.
ability right now. So that poses a sort of constraint on how much memory we can consume. I'm not saying you can't consume 2 gigs, but I'm saying you would want to be a little bit, you would want to test that and make sure it works until Golem becomes more sophisticated about its ability to sort of do dynamic rebalancing. And then the other constraint is the speed at which we can access and update in-memory data structures like maps.
Sure.
So big data structures, like, for example, let's take an in-memory cache that has 100,000 elements. That's actually that's actually not that easy to do. It's not easy to have a cache that can work with 100,000 elements, and you can do that actually, but it's again, you're really sort of pushing it, and you're going to eat into
Right.
significantly the CPU and the memory of the machine because caches have to store things in multiple ways. Like you've got to store it in a linear order if you want first in, first out eviction policies. And then also you've got to worry about timeouts, like you evicted. So a cache is like a very simple data structure, but when you want to scale it up to be able to handle a huge amount of data and you want to make it complex in the way that you look at that data and the way you evict it from the cache, it can actually consume a lot of CPU and memory. And it's the same thing here. We need to think through carefully because we've got so many submissions per second, right? Dozens of submissions per second. So that doesn't seem to be a problem. But how many different ways do we need to look at that data? How many different ways do we need to index it? When we add one new workflow into the system, how many maps do we have to update? How many linked lists do we need to add one to the size of? How many searches do we need to perform? And that's going to depend on how sophisticated and complex your policies are for deciding when to run these workflows and when to put them on hold and, per user, all that stuff. So just,
Got it.
I would say combination of understanding the number of workflows here and the imposition this might make on CPU and memory combined with all of the complexity associated with maintaining what is potentially many different views of the same data.
Got it. Yeah.
It's
Thanks.
like a
Thanks for.
database. If you add 20 different indexes on one table,
Right.
ouch, you're in
Yeah.
trouble.
Right.
It's the
Right.
same for this. It's going to depend a bit on the logic.
Got it.
All
No, yeah.
right. So,
Thanks for clarifying that.
yeah,
Yeah,
I think I'm sold on the idea of trying. I think we do need to flesh it out in a bit more detail, which would
for
be
sure.
similar to the document I did for the download component. But I think this is very promising. And I think it's quite likely it leads to a very simple, elegant, easy to develop, easy to maintain architecture that's going to give you a lot of flexible power in the way you implement these rationing policies. And then the next question I have is if there's any piece of this architecture that's more central and more important than Kafka here, it would be Dapper, I would say, because we got all these lines going into and out of Dapper. It truly is a central piece of this distributed system. So let's drill into a bit more what we're getting out of Dapper and how we might recreate that in a different way using an architecture built for Golem.
Yeah. Yeah, so for anyone, I don't know exactly how familiar people would be with Dapper and why one might use it, but I think we just briefly mentioned last time, and it's pretty straightforward. Is the category of tools that one might be using, such as a state store, may not always be Redis, and the pub sub broker may not always be Kafka, and so on and so forth. And so Dapper kind of provides an abstraction layer that would allow you to swap out, different components, providing those types of services without changing everything, that you're using to interface with them. So it sort of provides a semi-uniform API for those types of services that you can then knit together into something that's a bit more modular. Actually, my first blush on that was just that, well, the concept that we discussed in terms of this sort of workload manager, um, regarding the uniformity that comes with Golem, I suppose, in terms of the actual way in which you would implement individual components, already, I think, begins to buy you a little bit of that. But I suppose it does end up coming down to how do you actually design the APIs by which these components are then talking to each other that
Yeah.
would allow you to say, um, look, this pub sub broker needs a certain interface, but if you change all of the internal structure, of how you're how you're managing, something else like your, database or your state store or something
Yeah.
else, or at least the API that, interfaces with those, then that structure, I guess, is still something you have to think of. And I would imagine redesign in terms of the component model. But yeah, that's my, 2 cents
Yeah.
on what Dapper would be for. But
Okay.
yeah, yeah.
Yeah, because Dapper, it's really, I think it's a very increasingly comprehensive toolkit for building distributed applications. And it provides so many different benefits. So I was interested in what were the top things you went to Dapper for. And one of them, for it actually has workflows in there. Dapper has this concept of a
Yeah.
workflow. It had
Yeah.
all this different stuff in here. It's very
Yeah.
large.
Yes.
And I think what I'm hearing from you is one of the primary things you get out of Dapper is this level of abstraction from concrete implementations of your publish, subscribe, your key value store and whatnot. And that allows you to not have to worry about that stuff now, to just write your logic. And then later you can decide what you're going to plug these different services into.
Yeah, my concept for that was purely about modularity. There
Yes.
was nothing beyond that. But yeah, it's good to point out, as you said, the number of categories that they support,
Yeah.
including workflows and actors and so
Actors,
forth. Yeah,
secrets,
it's
like
pretty vast. Yeah, it's
distributed
pretty.
locks that you could do, distributed consensus. There's a lot
Yes.
of primitives here.
Yes.
It looks like a smorgasbord, a bazaar,
Yes, I only
solving all the
began to
sorts of
scratch
problems you run into.
the surface of its capabilities in my diagram. Yeah,
Yeah.
yeah,
All right. Well, that's good to know. So you're
yeah,
using it for modularity and abstraction.
yes,
And honestly, I wish that the WASM ecosystem were further along because they're obviously trying to get here. And let me explain why it matters to them. So WASM is being developed mostly by big cloud platforms out there, cloud computing platforms that have the ability to run serverless workers. So like AWS Lambda, that type of thing.
right,
And why they care about modularity and abstraction is because they want to be able to say to their clients, you don't need to worry about which database you want to use with your serverless workers. You don't need to worry about which queue you want to use with your serverless workers. You
right,
shouldn't even have to contaminate your code with those concerns. Right?
right.
That's a beautiful thing, in my opinion. Like, why
Yeah,
is it that all of our code is like import org.apache blah blah?
yeah,
It shouldn't be like that in an ideal world.
right,
It shouldn't be like that. And I think that these cloud providers of serverless workers, they really are thinking about that, and they're trying to think about what is the next phase of cloud native development look like. And one of the things we would want to do in that phase is to get rid of all of that. You should not have to decide in your code which queue or relational database or key value store or blob store or whatever you're going to plug
right,
into your application. You should be able to change that over time without changing your code if that's what you want. And the component model is really ideally suited to that. It's ideally suited for solving that exact problem. How? Well, because your application, your own component, can depend on some sort of interface that can be implemented by the cloud provider. And it could be implemented by multiple cloud providers, giving you cloud portability, but it could also be implemented by the same cloud provider in different ways. So they could say we have this sort of interface that gives you everything a key value store should have. And we have an implementation for DynamoDB, and we have an implementation for Redis, and we have an implementation for SQLite, and so forth. And they can give you that flexibility to choose which of those implementations you want to use with which of your components in which circumstances, and potentially, bill you by your use of that feature. So that's where they want to go, and that's why they want to go there. However, the reality is they're not there today. However, that said, there's a few things out there. So there's this WASM interface, this spec for a key value store called WASI key value. And that defines what a key value store should look like. And if you write your application to that definition, then any cloud provider could swap in any possible implementation of that key value store without you having to change the code that you wrote. And then there's WASI blob, which is similar for blob storage. And there is one for SQL as well, but that's not in a good shape. That's very early stage right now. The other ones are further along. And Golem actually supports WASI key value and WASI blob out of the box.
Nice.
There is something actually for Q as well. I don't know how far that is along. Golem does not support that yet, but I do feel like things are close enough that if you're willing to live on the bleeding edge, you
Yes.
might be able to use these WASM component model interfaces as
Interesting.
that layer of abstraction and modularity, which lets you plug in different things. And Golem is definitely headed in this direction. So there will be a
Nice.
point where we have implementations for WASI key value. We already do WASI blob. We already do WASI Q, or whatever they're calling their Q standard, WASI SQL,
Mm.
etc. And you can use these in your applications, and later you can decide how you want to hook them up. Do you want to self-host Postgres? Do you want to use a hosted Postgres? How do you want to hook this up to real life infrastructure later? And you can decide that differently in your tests than you do in your production application. That's the way Golem is headed, because I feel like this is a problem. This component model and these interfaces are a solution to a pervasive problem of infrastructure complexity and vendor lock-in and so many different things that we developers face when we go out there to build best practice cloud native applications. They're solving these problems in a way that I think is actually really good and can point the way to the future of cloud development.
That's really interesting because that was probably the component I had the least clarity on as to what would be, the way to think about either an alternative or does the problem evaporate? I think I was wondering if the problem that it solves almost evaporates, but this gives me a lot of insight now into how this might evolve that I didn't know about, and I imagine maybe given that these are obviously at an early stage, maybe many people weren't too aware when you were first discussing it. It gave me this concept of like, well, you can imagine like, the open source sort of version of Cloud Run or, a Lambda like
Yes.
thing like Knative having plugins to do this. But
Yes.
this seems to me like this will be the analog now for the or something that would be related to this sort of approach where you have these canonical interfaces that people can share because there's no point to rewrite these in most cases over and over. So that's really interesting because I had no idea how I was going to rethink the Dapper component. So I'm surprised we got into that today, but that's great.
Yeah, so I think what we've done in this session, since we have to wrap up now,
Yeah.
is basically we've thought about the Kafka part. We've identified why you were using that, and we've come up with an analog in the world of Golem, which is the workflow manager,
Yes.
which scales very, very well. Maybe not to any hypothetical future, but like a singleton workflow manager will be way more than sufficient from now, the starting point, up until wild, crazy success. When you have to think about sharding the workflow manager, you're already like everyone in the world is basically using BioRoastery. So I think that's a good problem to have.
Yeah. Right. Right.
And then the other thing we did is we took a look at Dapper and we identified the primary reason that you reach for Dapper, which is isolating you from infrastructure decisions. Like which component, which thing,
Yes.
which Redis are we going to plug in Redis or whatever we're going to plug in here. And that's great. And that's sort of satisfied by some of these WASI interfaces, not all of which exists, but they are coming along. Golem implements some of them, and which might be sufficiently ready over a relatively short time frame. And it's not like they block you, right? You can always build your own interface if you want to introduce this.
Right.
But having out of the box sort of time tested interfaces is great. And we have that in a few cases. And as time goes on, we're only going to have more and more of these things, and they're going to be more and more proven and more widely supported. You're going to be able to run stuff in, Fastly or Cloudflare or Golem or whatever, and use the exact same key value interface, the exact same blob storage interface, etc. So I think we've done a pretty good job with those two. And then we just need to think about, I think, some of the other things on the periphery of this diagram. Many of these will, I think, be already covered by design decisions we've made. So maybe what I will do is, if your homework is to prototype the download component,
Yes.
sketch out some code there and get
Yeah.
it running on Golem, then my homework is maybe just to think about the whole architecture and to come up with, at the very least, an architectural diagram that is one possible way to get us the benefits of your original architecture, but with embracing all the benefits of the WASM component model and durable computing.
Yes. And just before, regarding my homework, just before we signed off, I wanted to ask you, and maybe others would be interested as well. If people are interested in like doing sort of prototype examples with Golem, is it welcome to try to, even if you fail, contribute them to your Golem examples
That
repository,
would
or
be
is that
wonderful.
something?
We could definitely
Okay.
use more examples.
Okay. Yeah, I just wanted to try to, because probably the download service, if I get it right, is going to be sufficiently general that at least it could be an example, if not something that other people might,
Yes,
actually use in any sort of production scenario.
that would
So
be
I was just thinking
fantastic
if
to
I
have a
targeted
download
that, it would be
component.
more interesting. Yeah. So great. Yeah, it's good to know that you guys are, open to contributions
We
there,
would
and I'll
love to
take a look.
see more examples because they're how people get started
Yeah.
today.
Well, that's how I'm going to learn how to do it. So we'll see
Yes,
how properly. So yeah, we'll see how that goes. Great. Thanks a lot.
absolutely. All right. Thanks, Cameron. Great to have you back on. Look forward to our